Now I'm going to draw the top half of the decision tree for the robotic surgery study. So we're choosing between two robots, robot A and B in this example. I'm going to show each robot separately just so I can work through the math more easily and show you how it gets a single cost and a single quality for each of the two robots in the study. So remember that we start with this blue square decision node. In this case, we're choosing robot A. And then if we choose robot A, it goes into what's going to be a green circle. The circle's a chance node. So if you choose robot A, there's some chance that there's a hemorrhage associated with robot A, and then some chance that there's no hemorrhage associated with robot A. And those probabilities of hemorrhage and no hemorrhage, given that you're having surgery with robot A, have to sum to 1. The probabilities after a chance node always sum to 1. I'm going to color in the different parts of the tree so it looks just like we did in the triage example. So decision nodes, those are blue squares. Those are things we have to decide. So blue square, we choose robot A. That's something we decided. And the green circle, that's a chance node. So the green circle is something that nature decides. So if we choose robot A at the blue square, then at the green circle, nature chooses whether or not there's a hemorrhage associated with surgery with that robot, with that robotic surgeon, A. Underneath it, I'm just going to write the probabilities, just like we put in triage. So in this example, I just want to use a simple average. So we choose robot A, we'll say half the time there's a hemorrhage, and half the time there's no hemorrhage. 0.5 plus 0.5 equals 1, or 50% plus 50% equals 100%. Same idea. Now associated with each of these terminals, the red terminal triangles, is a cost and a quality associated with that outcome. So for robot A, we see there's two costs, depending on whether or not there's a hemorrhage. If you choose robot A and happen to have a hemorrhage, it's going to cost $70,000. If you choose robot A but do not have a hemorrhage, then that's going to be $80,000. Similarly, the qualities associated with hemorrhage and no hemorrhage could be different. So let's say you choose robot A and you have a hemorrhage, it's going to be $70,000 and you get a quality. If you choose robot A and there's no hemorrhage, we're going to say it's $80,000 for 3 qualities, quality adjusted life years. Now this top part for robot A just simplifies to a simple average. So if you took the average of $70,000 and $80,000, that would be $75,000, right? $70,000 plus $80,000. Take that quantity divided by 2, it's $75,000. That's the overall cost of robot A. What if you took a simple average of the qualities? Well, we would say 1 quality and 3 qualities, 1 plus 3 qualities is 4 qualities. Divide it by 2. 4 divided by 2, that's 2 qualities. The average would be 2 qualities associated with robot A. Now the goal here is to take these 2 costs and these 2 qualities at the end of the robot A branch and average them back into a single cost for robot A. So I have it listed here as the cost of A. And you can see here what I'm doing is I'm multiplying by 0.5, but remember that multiplying something by 1/2 is the same as dividing it by 2. So the expression I'm showing here for the cost of robot A, this would simplify into $70,000 plus $80,000. The quantity $70,000 plus $80,000 divided by 2. Multiplying something by 0.5 is the same as multiplying it by 1/2. When you multiply by 1/2, you're dividing by 2. So again, it just turns out, the simple average of $70,000 and $80,000 is $75,000. That's the cost of robot A. So now we average those 2 costs back into a single cost associated with robot A. And that's called rolling back a tree, right? Rolling back those multiple costs and qualities from the terminals back to the robot. So we start at the right-hand end of the tree and then we fold them back. So it's like we're collapsing it into just a single robot A outcome that has a single cost and a single quality for robot A. The quality is the same thing. Again, I'm multiplying each of the qualities by 0.5, but I could also just add them up and divide by 2. Just a simple average because it's the same probability for both of those. what's the average of one quali and three qualis? It's two qualis. This is going to come out to two qualis. I just want to show you all of the details of the calculation so that it flows into what happens when we have different probabilities of hemorrhage and no hemorrhage, like robot B. So the single cost associated with robot A was $75,000. The single quali associated with robot A is two qualis, $75,000, and two quality adjusted life years, one cost and one quali for robot A. So now we solve for the cost and the quality of robot A regardless of whether or not there's a hemorrhage. Hemorrhage just weights those outcomes or averages those multiple outcomes and folds it back to the robot. Now this is the bottom half of the tree. So the bottom half of the tree is where we choose robot B. And this one's no longer going to be a simple average because the probabilities of hemorrhage and no hemorrhage will be different from one another. And for robot B, it's going to be what's called a weighted average. And a weighted average, you'll see it's just like a simple average, except the probabilities become weights that weight the cost and the quality more towards the hemorrhage or no hemorrhage branch. Whichever one has the higher probability weight, that's what it's going to be closer to. Now you see it's symmetrical to the top robot. And I'll draw in the red terminal triangles, the outcomes here. And then so if you choose robot B and it has a hemorrhage, we're going to say that's $100,000. But if you choose robot B and there's no hemorrhage, that's $80,000. So again, these two costs are going to take a weighted average and roll back into a single cost. If you choose robot B and there's a hemorrhage, let's say there's one quality adjusted life year, choose robot B, but there's no hemorrhage, we'll say that's three quality adjusted life years. And now I'm going to add in the probabilities. So this is just like in triage where the probability of hemorrhage for robot B is going to be set at 0.25. No hemorrhage has to be 1 minus 0.25, so that has to be 0.75. Remember that the probabilities associated with the different branches coming off of the chance node, coming off of the green circle, have to sum to 1. So 25% and 75% equals 100%, or 0.25 plus 0.75 equals 1.0. Now you can see the formula for the cost of robot B is going to be similar to the formula for the cost of robot A, except it's no longer going to result in a simple average because those probabilities are different from each other. For robot B, there's a different probability of hemorrhage versus no hemorrhage. The cost and the qualities are still going to average, but they're going to be weighted more closely towards the cost and the qualities associated with no hemorrhage because that probability weight of 0.75 is higher than the probability weight of 0.25. In robot A, the cost and the qualities were exactly halfway between the values for hemorrhage and no hemorrhage. For robot B, the values are going to still be between the cost and the qualities for hemorrhage and no hemorrhage, but the cost and the qualities will be closer to what we see for no hemorrhage because of the higher probability weight given to no hemorrhage. You can see me take the weighted average of the costs there, and I'm going to calculate a single cost associated with robot B. That's going to be $85,000. Remember, we said it's got to be between $80,000 and $100,000, closer to the $80,000 because of the higher probability weight on no hemorrhage. And the single quality associated with robot B, that's also going to be another weighted average. So what is this? It's going to be the probability weight of hemorrhage, 0.25, times the cost of hemorrhage. That's going to be times the quality of hemorrhage. That's going to be 1. 0.25 times 1. Take that quantity, and then we're going to add to it 0.75 times the quality of no hemorrhage, which is 3. So 0.75 times 3. Now what is this going to equal? So it has to be between 1 quality and 3 qualities, but it has to be closer to 3 qualities because of the higher probability weight of 0.75. And then once you get the final quality associated with robot B, now we have one cost and one quality for each of the two robots. Now we could look at the ICER of robot B. Right? The ICER is just the change in cost over change in quality. Now that we've showed how to roll back the tree, you're going to take these four numbers, these two costs, and these two quality values, and then you could calculate the ICER associated with robot B.